We are Lab Group 4 in ECI 100 Fluid Mechanics. Our fluid phenomenon is vortex shedding as it occurs in flow. To begin, we must first understand the concept of fluid flow itself. Fluid flow can be defined as the motion of a fluid body due to a body or surface forces acting on it. Fluid flow has many characteristics. For example, it can be external or internal, laminar or turbulent, or steady or unsteady. No matter which characteristics a fluid holds, it is subject to a fluid phenomena known as vortex shedding. So what is vortex shedding? Vortex shedding is the formation of an oscillatory wake resulting from a fluid being separated by an obstacle in its path. Shedding occurs when the boundary layer of the fluid departs from the surface of a given obstacle. Why does this happen? The region directly downstream of the obstacle has a lower pressure than the surrounding fluid, generating a vacuum for recently shed vortices to fill. As demonstrated in this graphic of flow around a cylinder, the alternating vortices from above and below the cylinder apply a force on the cylinder perpendicular to the direction of the flow. In addition to the direction of the vortices, the characteristics of the vortices will vary in shape and frequency, depending on the size and shape of the obstacle it impacts. Looking at the demonstration of two cylinders of different sizes as an example, the shedding of the vortices are inversely proportional to the cylinder's diameter. As you can see here, the larger diameter will result in a smaller oscillation frequency than the smaller cylinder. If the obstacle is not fixed in place, it will oscillate in its simple harmonic motion at the same frequency as the formation of the vortices. The frequency of this oscillation is dependent on the shape of the obstacle and the velocity impacting the object. Vortex shedding varies with varying velocity. The velocity of the flow is important because the higher the flow rate, the higher the Reynolds number. We aren't going to see any vortex shedding with a Reynolds number under 40 because the flow is too laminar. For one of our examples, captured at Mount Occam, we calculated the frequency of the vortex shedding to be 5 vortices for every 3 seconds. This is approximately 1.7 vortices per second. We then calculated the diameter of the cylindrical shape using the curve of the rock. This was about 150 millimeters. By multiplying the two together, we should get a velocity of the flow to be 1.25 meters per second. Another example was captured at the North Fork of the American River. The average velocity in the river flow is 5.25 meters per second, and the rock had a diameter of 0.273 meters. This results in a Reynolds number of 1,426.67, which is extremely turbulent. Reynolds number at Mount Occam was approximately 186.64. The Reynolds number for the American River was much higher, indicating that it was much more turbulent. This indicates that the vortices will vary more in size and have a higher frequency than the Occam Mountain River. Vortex shedding was previously demonstrated in Lab 2 through visualization with rhodamine dye of water flowing around a cylinder. As you can see in this clip, streak lines shown by the pink dye illustrate the stagnation of the fluid just upstream of the cylinder. The flow along the boundary layer of the cylinder and the departure of the streak lines from the obstacle's surface just downstream of the center of the cylinder. At this point, we can see the vortices falling into a lower pressure area directly downstream from the cylinder. The alternation of the vortices shed into a lower region generates an oscillatory wake in the flow downstream of the cylinder. Vortex shedding is also prevalent in a variety of examples in nature. In the next few clips, we will take a look at vortex shedding apparent in the American River. In this first video, we can see flow around a stick drawn slowly upstream in the water. The vortices look similar to those in the rhodamine dye demo due to a similarity in flow rate, fluid type, and shape of the obstacle around which the fluid is flowing. Here we have a second example of water flowing around a rock. The difference in shedding frequency is apparent. Water is not the only fluid in which vortex shedding occurs and is relevant. Our next two examples show vortex shedding in the air, visualized by the movement of smoke and steam. The soot particles and smoke allow us to view the movement of carbon dioxide and water vapor gases formed by combustion. As we all know, hot air expands and rises, and therefore the smoke travels in the general upward direction. Smoke trails are generally quite turbulent. In consideration of this within the reference of the Reynolds number, the inertial forces dominate over the viscous forces. Although the higher velocity correlates to the higher Reynolds number, the viscosity of air, similar to smoke, is much lower than that of water, decreasing the denominator of the Reynolds number and increasing the turbulence of the fluid. In an attempt to show vortex shedding due to the interaction with an obstacle instead of general turbulence, we place the straw close to the source of the smoke, where the flow is more laminar, and less influenced by convection currents in the air. With regards to vortex shedding, we can see the frequency of vortices in the smoke is relatively low in comparison to the water. As mentioned earlier, this is because of the low linear velocity of the fluid, while vortices are still able to form due to the low viscosity of air. However, we can still see the alternating vortices due to the pressure drops on the downstream side of the obstacle. We can similarly see the phenomenon of vortex shedding in air by showing the behavior of steam as it exits a tea kettle. Steam is visible to us in the form of a water vapor. Similar to smoke in that its viscosity of water vapor is less than liquid water, and its more turbulent flow in general makes it comparable to smoke. Now that we have shown the prevalence of vortex shedding in two common mediums, we will take a look at why this phenomenon matters. It's important to consider the concept of vortex shedding when constructing structures that are tall and skinny. Forces can be caused by pressure differentials and oscillations. And if the frequency of the oscillation results in a vibration which matches the harmonic frequency of the building, it can cause serious damage to the building structure. Spirals are added to chimneys in order to prevent vortex shedding, which can cause structural failure. This is an important consideration for any tall and slim structures, which are subjected to loading and most commonly from wind. Another reason vortex shedding matters is because of the dangers it causes to whitewater rafters. When you fall out of a raft, the force that causes vortex shedding to occur can also pull you into the pressure of the differential and hold you there. We can see this in the footage of a leaf moving against the flow of the stream due to vortex shedding. There are a couple key takeaways that we should take about vortex shedding. One is that vortex shedding occurs in a certain range of Reynolds numbers. It cannot occur in all types of flow. We can find the Reynolds numbers for different mediums, and we were able to perform vortex shedding demonstrations in water and air at different velocities, viscosities, and length scales, which contribute to the Reynolds number. Oscillations cause periodic force on an object perpendicular to the motion of flow. This is an important design consideration. Thank you for listening.